Welcome! Today, we're diving into a really fascinating problem in biomedical science, and we're going to explore it using an AI-powered simulator that honestly acts a lot like a detective for the body's hidden signals. So here's the core problem we're tackling. How do you isolate a tiny but super important signal when it's right next to a massive source of interference? It's kind of like trying to hear a pin drop during a rock concert. Okay, so first things first, let's meet our two main players in the stomma, the signal we desperately want to hear and the noise that's just completely drowning it out. On one side, we have what we're calling the whisper. It's this tiny electrical signal from the diaphragm muscle. It's called the SEMG di, and it is incredibly weak, but it's absolutely crucial for monitoring how a person is breathing. And then on the other side, you've got the heart's ECG signal. Now, because the heart is so close to the diaphragm, its electrical signal is way, way stronger. We're talking up to 8 times stronger. This is the shout that we have to somehow see past. What's really cool about this slide is how it shows you just how much location matters. That top signal, that's from a sensor placed right over the muscle. It's strong, it's clear. But the bottom one is from a sensor that's farther away, and you can see how the signal just fades into this faint little murmur. So what happens when you mix the whisper, the shout, and all that other random background noise together? Well, you get a real mess. This right here, this is our target. Think of it as the victim in our little mystery. It's the pure electrical signal from the diaphragm. And notice how it comes in these nice bursts, perfectly in sync with breathing. This is the clean data we need. And here's our main suspect, the ECG. It's this loud, powerful, repeating signal from the heart that just completely stomps all over our target. You see those regular, powerful spikes? That's the main source of contamination. And then you've just got chaos. Random electrical noise from other muscles, from the patient moving, from the equipment itself. It's like a layer of static that just garbles the whole conversation. And this is the result. This is our crime scene. It's a messy, contaminated signal where that crucial breathing data is totally, completely lost in the noise. I mean, looking at this, you would have absolutely no idea what the real breathing pattern is. So, to solve this mystery, scientists developed a really clever detective, an algorithm that's specifically designed to untangle this mess and find that hidden signal. It's called the Progressive Fast ICA Peel-Off Method, or just PFP for short. And you should really think of it like a signal detective, meticulously sifting through all that noisy data to find clues, identify the culprits, and ultimately rescue our victim. Now, this is a crucial point. The reason we can even explore this so well is thanks to an AI-generated simulator. This simulator basically acts as our detective's case file, and it lets us test and reproduce the very techniques that were described in the original research paper. Okay, so how does this detective actually do its job? How does it conduct its investigation? Let's take a look at how it peels back the layers to get from that messy mixture to a clean signal. You know, the process is a lot like peeling an onion. The PFP algorithm scans the entire mixed signal, and it identifies the loudest component, which is almost always going to be that heart signal, the ECG. Then it just mathematically subtracts it. And then it does the whole thing over again on what's left behind, just layer by layer. And this graph brilliantly illustrates the investigation in action. Just look at the red line. With every single peel-off round, the signal-to-interference ratio, which is really just a fancy way of saying clarity, improves dramatically. The whisper is finally starting to be heard. But the big question is our detective actually any good? To find out, let's look at the evidence and see how it stacks up against some of the older, more conventional methods. All right, first up, signal clarity. Now, the other methods, the ones in blue and green, you can see they really struggle as the noise gets worse. Their lines even dip below 0, which means they're actually adding more noise than signal. But look at the red line for our PFP detective. It just stays stable and positive, delivering a clear signal no matter how loud all that interference gets. Second, let's talk about accuracy. I mean, how well does the extracted signal actually match the original, clean one? Well, here again, the PFP method is an absolute star. That red line shows it achieves near-perfect correlation, near-perfect accuracy, even in the toughest, noisiest cases where all the other methods just fail. And here it is, the verdict. This is the big reveal. On top, you've got that messy, contaminated signal we started with. And right there in the middle, that's the clean breathing signal, successfully rescued by our PFP detective. It is an almost perfect match to the clean reference signal you see at the bottom. So this is all really cool tech. But why does solving the signal mystery actually matter in the real world? Well, the implications are pretty huge. What you're looking at here is the ultimate proof. The blue dashed line shows the rhythm of the signal our detective extracted, and it aligns just beautifully with the red dashed line, which is the actual pattern of breathing. The whisper has been heard, loud and clear. This kind of technology has massive potential. It could let doctors non-invasively monitor breathing in very fragile ICU patients, maybe help diagnose respiratory illnesses much earlier, and even improve the control of advanced prosthetics. Plus, building open simulators like this one makes science itself more transparent and accessible for everyone. And it really leaves you wondering, doesn't it? As our AI signal detectives get smarter and smarter, what other secrets of the human body, secrets that are currently just drowned out by noise, are they about to uncover for us next?